In this week's video, I want to go over how to automate a Haas CNC lathe. This is a video I wish existed when I did this work myself. So I just wanted to do a quick overview of the system and how it's integrated and incorporated into the lathe for automation that is hands-free and runs lights out. This is a DIY automation that we did ourselves in-house using a Universal Robotics arm, and most of the other components were sourced from McMaster-Carr or 3D printed. I'll walk you through the different components of the system, how it's integrated into the Haas machine, but any of the fine details, G-code programming, or specific part numbers you'll have to source yourself for your own shop. The key benefits of automating a Haas machine like this is it eliminates all the standby time of your operator and reduces any damage that would occur in the parts catcher system that's included with Haas machines. It allows for individual handling of every part and perfect part tracking through a system grid. Here in California, labor is at an all-time high, and it's very important to us to run a lean manufacturing shop and keep the costs down for operators. I know this isn't our usual video, but I wanted to make a video for other machinists and small machine shops on how to integrate a Universal Robotics arm and get it working with lights out manufacturing for a small shop environment. So let's get started, and I'll show you how we set up our lathe. So what we have set up here is a Universal Robotics arm mounted to a steel welded table. It includes a parts washer, a grid array that we can change part size depending on what we're making. On the end of the Universal Robotics arm, we have an electronic gripper with interchangeable inserts, which we change based on the part we're making, and all of that is controlled with a few standardized programs. So to integrate the robot, we first need to make a couple connections. So you'll see our incoming air line here. We split it off, one going to the lathe, and then the second coming to a regulator. And then this is going to power our pneumatic water pump, and then also the air dry off for the part washer. So to allow the Universal Robotics controller to start the CNC machine, there's two ways you can do that. First, you can program the robot to literally physically press the start button. A lot of machine shops do that because it's really convenient and easy. But if you integrate it into the electronics, there is a lot less wear on the start button on the machine, less downtime while the machine is pressing the button, and it allows the robot to continuously work on the part and not worry about starting the machine. It's a much faster cycle time, and a better way to do it is to integrate directly into the motherboard. So you will need to purchase the M25 option for your lathe. So this is something you can buy from Haas, I think on their website, and you'll just have to have it activated for your machine. So on this ST-20Y, it's going to be right here. So opening this lower control panel, this is your in-out kind of I/O board. And right over here, you'll see this connection here that says M25. So you can pull that connector out and then wire in your control. So that will give access for the Universal Robotics to control the start of the machine. But basically, the machine will send out a command to the robot saying that the part is complete. But we don't want to depend just on that, because there's no real difference between that code and a failure or the end of a production cycle. So what you can see here is we have an additional proximity sensor that will monitor if the door is open. So this is just an extra safety verification that will indicate that the door is completely open. It will also act as a switch to know when the door is closed and that the CNC machine has started on its next job. If there is an error or the machine is paused and the door doesn't close, the robot will wait for that to happen. With automation, it's really important to have several redundancies so that in a failure mode, you don't have a collision or something go terribly, terribly wrong. Especially with spinning lathes, it's really critical to be very safe. So there are a couple considerations when running a automation process on a lathe that has a very high cycle count. So what we prefer to do here is use solenoids. So you can see these solenoids here. They are electronically actuated, but we like to use air solenoids and a pneumatic pump instead of an electronic pump, because the duty cycle on a inexpensive electronic pump will wear out the motor very, very quickly. We're doing, hundreds of thousands of cycles on this machine annually. So it's really, really important to have very robust long-term systems. So each of these solenoids has an in, out, and then an electronic control. These control wires will be run into the control box here. So this is where we're going to wire in our solenoids and sensors. So you can see here, we have wired in digital inputs, digital outputs, and sensor controls. So in the control box, you'll see digital outputs. Digital outputs will be used to control the solenoids and any external controls that you need the programs to be able to modify. So that will also be your shunt gripper. So we'll have one set of wires to actuate close and one set of wires to actuate open. And then we have the air solenoid for the water pump and the air solenoid for the air blast. Then in here we also have digital inputs. So that will be where your sensors are coming. So right here. So that's going to be your proximity sensor, and then also the feedback from the gripper of the shunt gripper. This lets us know when the CNC machine has finished with the part, or when the door is open or the door is closed. So these are really important for controlling the system and not having any collision errors where the robot goes to the machine on a failure and maybe breaks the parts. The last thing you'll need to connect is a sub-spindle release. So this allows you to remove the part from the sub-spindle. This is something the robot has to be able to control. So we use this powered relay to create a short. Then we take that wire and we actually directly integrate it into the sub-spindle pedal. So the sub-spindle pedal here simply creates a short to indicate to open the sub-spindle. So we simply wire this in and connect it across both terminals. And then when you need to activate the sub-spindle, the robot is able to cause that short, which then activates it. So one of the things that makes automating a lathe so easy is that your parts are always on the center line of the spindles. So that means you always know where you're picking it up. Unlike a CNC machine, like a vertical CNC machine, where you have a vise and the part could be on the left side, the right side, or you have different setups entirely, this is always going to be based around a chuck. So we use the Royal collet system, which allows us to quickly change the inserts from both the main and sub-spindle. And then when the sub-spindle is released, it's a very clean, zero movement surface. So the surface opens, but the chuck itself doesn't expand out or in. So this makes it so you can bring the gripper right up to the surface of that chuck and open the sub-spindle, and you're not gonna have any pushing or interference between the chuck and the gripper. So you'll see here, we have this spring. So this allows when you open the sub-spindle that it'll push the part out of the collet into the gripper. So after you open the sub-spindle and push the part into the gripper, you then tighten the gripper on the part. This is a very easy and consistent way to get the parts out of the sub-spindle into the gripper. And for those of you who aren't familiar with lathes, your incoming stock material is going to be here on the main spindle. We're going to cut op 1 on this part, and then the sub-spindle is going to approach, hold the part, we're going to cut it off, and then the sub-spindle will come across the machine here and we'll finish it. And so the parts will always be finished on the sub-spindle, not the main spindle. And that will have both operations done on each part. For the robotic pickup, it's important to keep the sub-spindle the same every time. So in your G-code, you'll want to move the sub-spindle to a specific reference plane so that your robotic arm knows where to be every time you release a part. So with those connections made, you're going to be able to start assembling the system. I do recommend getting a solids model of the robotic arm, getting a solids model of your lathe, and checking all of your dimensions. Just note, you can't take the robotic arm to full extension. The mechanics need to have a slight bend to have full kinematic motion. But it is ideal to choose the smallest possible robotic arm. The larger the arm gets, the more cumbersome and difficult it is to work with. So starting with this table, it's a very heavy-duty, 1/4-inch welded steel table, and we've bolted it directly to the ground. This means we're not going to get any movement between the machine and the table itself, which is going to keep things very consistent over time. If there are any movements, like we moved the CNC machine, we will just simply readjust the programs that we have. The grid pattern we have set up here allows the parts to get dropped off in consecutive order. But what this does is this keeps track of which part is in the right order, so that if we do see a discrepancy in measurement and check every maybe 10 parts, we can backtrack and find where the part tolerances got out of whack. So then everything before that bad part is good and everything after the bad part is bad. So this eliminates any sorting or measurements of every part and allows us to really batch safely and securely. So depending on the part size we're running, we have a couple different configurations we can install. So right here is our standard size. So it's great for small buttons, anything that fits within this envelope size. But if we do a larger, like a product knob or large foot, we can use one of these trays and simply place it over the top. This will require you to use a different program for every style of offload, because it's going to be at a different pitch and a different height. Now we also have an option for bolts and screws. So we use this for the standoffs in the Sentinel, and this goes on here. After the grid is full of standoffs, you can see here we have drainage holes. You can take this rack directly to the sink and do a full rinse. So the rinse chamber is something that we made ourselves. It's very easy and straightforward to make your own. It's just a 3D printed enclosure that goes through the top of the table. And then we have in here coolant jet blades to distribute the water for clearing it, and also for the air blasts. And then we do the air blast above the water so that any drips we get from the water don't drip into the air blast when it's cycling. The lowest portion here of the parts washer is also removable so that you can get the bucket of water out easily on the daily change. The water pump we have here is pneumatically actuated, so there's no on-off duty cycle that's wearing out with this product. These are really, really great for a process like this because it's pneumatically powered, and then we have that solenoid control for it. It's very consistent and inexpensive. So the gripper we have is an electronic shunt gripper, which means you have to power it open and power it closed when you're using it. It is not a single temporary actuation, but instead it requires the controller to be applying pressure throughout the process. So what we have here is different grippers. So you can see the different part numbers here. And each of these grippers is set up for a specific part. So depending on what we're running, we just simply change the gripper, and that's the only changing variable in the program, because the reference point to the sub-spindle is consistent from part to part. So you can see here, we have our 3D printed insert that is mounted into an aluminum gripper set. These gripper sets are replaceable, and we customize it to hold our specific 3D prints. This allows us to accommodate any of our parts we make here at MSB. Now on the side of the gripper, we have a force selection. So for most of our parts, we only need a 25-pound force, but on larger product feet like the Sentinel feet or amplifier feet, we will turn that up to 75 or 100 depending. There is a lot of inertia moving big, heavy stainless steel parts like that around, so it's good to have that option available. The wire is then simply routed down the robot and then directed into the control box. So when it comes to programming modern robotics, it's easier than ever. You have very basic GUI code writing programs like this, where you simply drag and drop the different functions you want. And to program a robot like this, which is also known as a cobot, it's simple as pressing the button on the controller and then just grabbing the robot and moving it into place. So all of these joints are easy to move just by hand. So you can move the robot to wherever you want it, let go, and it's now in place. This is why programming is actually the easiest part of this system. The hardest part is going to be implementing all the hardware and electrical connections. But when it comes to programming, it's really just a fun project that takes a little time to get dialed in correctly. So in our program list here, we will load a program. So we only have a couple programs on this machine. And these 4 programs run all of our parts. So the rinse dry cycle is simply the cycle of when the arm is here above the washing machine that runs through that. So we don't have to program it for every part. The unload lathe default is the one for our normal default grid. Then we have a long parts program, which does our standoffs and long bolts. And then we have a large parts, which does the larger grid array. So we really dialed in these simple 4 programs, and they run literally dozens of parts that are completely different because we've standardized on the interface between the robotic gripper and the sub-spindle. So by simply swapping out the gripper inserts and the Royal Chuck collets, we're able to change from one job to another in mere minutes. I hope this video is helpful and maybe inspires you to implement automation on a lathe in your own shop. We've found it to be immensely helpful, and it is one of our favorite implementations of automation we've had to date. Thanks for joining me today, and I hope you found this helpful.